Let me just summarize what we did earlier today. Just see. Okay, so this is the member that we already discussed. So I'll call that as first example or type 1. Are you able to hear me? Yeah. Okay, good. So that is the axial bar or the column bar because we put it under tension. All that we have to do for the column is to reverse the direction, which is what we will explore towards the end of the slide. So and typical examples of such applications, whether in tension or compression, are in the stringers in the wings. As you see in this particular aircraft, typically for all flights, for most of the phases, you will have the top under compression. So all stringers which are on the top are like beam-like structures or rod-like structures, which are typically under compression, and therefore we would rather call them as columns. But we are putting them all together as part of one-dimensional structures, which we call as beams. But the conventional way of calling such compressive members are columns. On the other hand, if you look at the bottom portion that is typically under tension, this is essentially because of the conventional lift distribution that we have, upwards bending, so the tip goes upwards, which means that the bottom stringers are all under tension. So both of those are included in this particular slide. Similarly, of course, in the fuselage also you have stringers which are running through the length that you see over here. Okay. So two cameras and making sure that it's seen in both. Okay, so that depending of course on the load, which is essentially depends on the tail, which is either adding to the lift of the wing or subtracting to the lift from the wing, which depends on the actual design features from the aerodynamics point of view and also the stability and control point of view. Therefore, the bending of the fuselage may be either upwards or downwards. And as we already indicated, this can be dealt with as a simply supported beam, supported at the wing and the horizontal tail. And we will also have an overhang from the wing onwards towards the nose of a conventional aircraft. Many aircraft will also have a canard, which means that you have a triple support that you're talking about. The overhang will not be too much in that case. Okay, so that's the example. So whether it's the wing, tail, which are the aerodynamic surfaces, or the fuselage that you see, you will have stringers. In addition to stringers, the spars, also especially the spar caps, will behave in a very, very similar manner as well as axial bar columns. For example, if it's an I section for the spar, the top flange will be under compression, while the bottom flange will be under tension, both of which are covered in this particular slide. This is just a summary of what we expressed in the whiteboard. I was, of course, using the Apple Freeform as the whiteboard over there. Let's go ahead. We, as always, looked at those four bucketing variables. That is the four important quantities which are used to describe the mechanical state of any structure, including this axial bar or column. And those are the loads, the stresses, the strains, and the deformation. In the example that we saw, we were given the load and we wanted to determine the deformation. So we took three steps in order to do that, which included those three equations, namely the equilibrium depending on the natural laws, the constitutive law depending on the material, and the kinematics, which depended on the geometry. Okay, so once we combined those three equations, we were able to relate the loads with the deformation, which is very similar to what we will do in the other three cases as well. that examples we will take forward in the next few slides. Now, before that, as I said, I wanted to summarize this. So you see in this particular thing, we talked about the load, which is F1, the stress, which is sigma 11. So we related that through the equilibrium equation F11 equal to A times sigma 11. Then we brought in the strain as well, which is, I should write capital gamma 11 here. It's not epsilon 11, which we are using for a different thing. So apologize for that. That should be gamma 11. So sigma 11 to gamma 11, the relationship, as was pointed by one of you, is 1 by E, is the coefficient there, proportionality. And of course, we also stated the assumptions involved that the other stresses are zero, and it's an isotropic material as well, to ensure that there are no other couplings. And finally, we wanted to introduce the last variable, which is the displacement, one particular measure number, namely U1. And when we correlated that, we had the linear kinematics, which also we said is something not really applicable in aerospace structures, because the displacements like U1 are fairly large. You would have observed how much the wingtip deflects by during flight, and especially during takeoff and landing, and therefore U1 values are fairly large, which means that epsilon or rather gamma 11 equal to U1 comma 1 is not a right approximation. Are you able to see my laser pointer, the red one? Yeah, okay, thanks. So that's what uh, that's a linear approximation. As I said, you need to include at least the quadratic terms there in order to have a more accurate representation of that. But here, it's only illustration of what we are trying to do. So just like we have a linear model for the material, we have a linear model for the kinematics. So these are the two which typically become nonlinear in a problem because of geometric nonlinearity. Almost all flight vehicle structures will have this equation in reality to be nonlinear, and that's what is typically considered in any structural analysis. On the other hand, this is reasonably okay to consider a linear model. As we saw, material linearity works until the proportionality limit for metals and composites. So typically, since we are operating in that regime, this might be a good enough thing to be considered, unless we are looking at actual failure and going towards the end of that. Yeah. So coming back to what we're doing over here, we saw that once we combine those three equations, we ended up with this particular equation that you see over here, namely F1 equal to EA times dou U1 by dou X1, which we can also write more simply as U1 comma 1. And once we have that, as Nafis pointed out, we could integrate for U1 and solve for U1 using the boundary condition, which in that example that I showed on the whiteboard was fixed at this end, and therefore we knew U1 equal to 0 at this particular end. Now, the important thing that I already mentioned is that one is a material property, namely Young's modulus, the other is a geometric property. But what I did not mention is that that particular geometric property, always, as we said, the geometric property depends on both size and shape in general. But in this case, it depends only on the size and not the shape, because that same A, the area of cross section, can be distributed either as a rectangular or square cross section, a circular cross section, or I section, whatever it is. So depending upon the problem, we can have various possibilities, and all of them will give the same result as far as U1 for a given F1 is concerned. So there is no preference as such for the particular shape of the cross section as far as axial members in tension are concerned. So you would see that you would go for the simplest shape for members which are predominantly subjected to tension, like the bottom stringers and the bottom spar caps, you really have no need to go in a particular way from a structural point of view. So non-structural considerations will take account of that. But of course, instead of this being a beluga, if it were a fighter aircraft performing certain maneuvers where the bending in the other direction becomes important, which is also important in other aircraft when it's on the ground, but the amount of load is much lesser because the lift distribution is of the order of the weight of the entire aircraft, whereas the downward distribution on the ground while the aircraft is in the hangar is mostly just coming from the weight of the wing itself, and of course what is attached to the wing, like the engines and the landing gear in this case, etc. So you would see that in such a situation, you will have the thing that is to be taken care of, the bending in the other direction. But since it's very small, unless it is an aircraft which has to maneuver in certain very complex ways, so that the lift distribution in the other direction also becomes a critical situation in the VN diagram to take care of. So that is as far as the F1 U1 relationship is concerned. And here you see this is what we have as far as tension is concerned. So this conclusion that there's no preferred shape is only for those members which are predominantly under tension. On the other hand, when we go to members which are also subjected to compression, or where compression is the dominant load. So as we saw in the stringers on the top or the spar caps on the top, then the way we take into account that mathematically, as you already know, is tension is positive F1 and compression is negative F1, which is what I've written as F1 is lesser than 0. So in such a situation, there is, as if F1 becomes large enough, there is a possibility of moving towards elastic instability, which we called as buckling. And that possibility can be either in the form of flexural buckling or torsional buckling, which you have discussed also before, that if the wing under consideration has a very low torsional stiffness, but reasonably good bending stiffness in both directions, then there is a possibility that when there is a compressive load, that compressive load will actually make it to buckle in the torsion rather than under bending. So this is something that is important to be taken care of. You should know based on the relative orders of magnitude of torsional stiffness and bending stiffness. You know also again bending stiffness in two different directions, bending along the chord and the bending along the this is the bending along the chord, and this is the bending about the vertical axis, which is because of the drag. So now one of them is dominant because one L by D ratios are larger than one. The other also because the chord is much larger compared to the thickness of the airfoil, and therefore from both the geometry as well as the load point of view, you would see that this bending is not that much of a concern, and the bending stiffness is fairly large and the loads are small, and therefore you would not have that much of a issue as far as buckling in that mode is concerned. The more common buckling would be the buckling in flexure, which happens for a lot of the panels, and we operate in the post-buckling regime. But right now, we're not talking of panels, we're talking of just the stringers that you see over here as an example of the axial column. And when you have such a situation, you could increase the buckling strength in multiple ways. So in the simplest buckling formula, which you may not have encountered, is pi squared EI by L squared. Depends, of course, also on the boundary condition. So depending on that, there will be a constant multiplying this expression. But essentially, it's proportional to the bending stiffness, EI, and it is also inversely proportional to the length of the structure itself. And that is, of course, the first buckling mode, that is the buckling load under that. So if you want to increase that buckling strength and therefore delay the buckling or even completely avoid the buckling, then there are multiple ways to do that because the quantities that it depends on are E, I, and L squared. And I, the moment of inertia, can be improved by going to an appropriate shape. We saw that as far as this equation is concerned, it depends only on the size, namely the area of cross section A. But once I comes into picture because of the possibility of buckling, then you have a preference for the shape also. It's not just the size, that is how much of area of cross section you have, but how you redistribute that within the cross section. So that becomes critical as well. So there are multiple ways in which the buckling strength can be increased. The first one, as you see, is in terms of the transverse supports that we have, so which are called as the ribs in the case of the wing or the tail, and they're called as, of course, the bulkheads or frames or rings in the case of the fuselage. Now, if you space those rings close apart, then the possibility of buckling is reduced. Similarly, if you reduce that in the case of the wings by bringing the ribs closer to each other, then again you can avoid buckling or delay it. So that is one possibility. That's what here it is said. Transverse supports, that is ribs in the wings or the frames in the fuselage, will shorten the length of the buckle board, and therefore that is something to be remembered. The second one way of increasing the buckling strength is by, depending on whether it's going to be flexural buckling or torsional buckling, we will increase that particular stiffness. The reason why it's flexural buckling is because the bending stiffness is very low in that particular direction, and therefore, in order to make it viable, we will have to increase the bending stiffness in that direction. On the other hand, if it is buckling in the torsional mode, we have to increase the torsional stiffness so that that will be avoided, and which can be done again based on the cross-sectional shape, just like we had an I section which can avoid possibility of a flexural buckling. A closed box beam would, or even a circular beam for that matter, which is hollow, will increase the torsional stiffness for the same area. So in other words, keeping the size same and the shape is different. So then you have the torsional buckling over there. Uh, I just want to confirm that you're not hearing any echo. Is it fine?
We are hearing a echo.
You're hearing an echo, is it? Oops.
But it's very small. I think it's fine.
Okay. Is it slightly better now?
Yeah, it's fine, sir. It's fine.
Oops. Just let me know if the echo is gone now.
Yeah, yeah. No, it is okay. There is no echo.
How about now? Is it good? Is it good?
Now it is.
Yeah.
You can hear us?
Any
Yeah, yeah.
echo?
Yeah, yeah. There is no echo, sir.
Can you hear any echo now?
No, there is no echo. Can you hear us?
Can you just speak? Let me see if I can hear it.
Yeah, can you hear us?
Maybe is the microphone setting correct? The microphone is after you.
Yeah.
Are
Microphone.
you able to hear me?
Yeah.
Yeah, microphone is fine.
Yes.
Okay, good. Thank you. And no echo, right? Okay. Can you hear me now?
Yes, sir.
Is the
We can,
is the echo bearable?
yeah, there is no echo.
Okay, great. Okay, thank you. Sorry for the interruption. So let's continue. So I think we are done with this axial bar column example. If there are any questions on this, I'd be happy to answer that. Otherwise, we'll go to the second example.
I think we're good.
Okay. Okay, now we come to the second example. You can ignore the homeworks here because we are already in the last week. So This is usually the homeworks that I give for the class, but I don't think we have time to get that done. So the only homework, two homeworks that we already have is what you'll be presenting on Thursday. Maybe on Wednesday, when you do the dress rehearsal, we can also finish off the other example, that other homework that we had, so that the last day, Thursday, is just left for the final salon. Okay, is that all right? Does it seem okay? Yeah. Okay. So now the second example that we will take up is a torsional member. In other words, we're going to be applying a torque. So if you see over here, I think you can see a gray cursor, right? Yeah. Okay. So we will be applying a torque. So the structure is very, very similar, but of course there'll be certain preferences for size and shape, which we will get into shortly. In terms of the length being much larger compared to the cross-sectional dimensions, once again, you have the same kind of geometry, but what is preferred within the cross-section, we will come to later. Now, the load that is applied is the torque. And just like there, the axial force, we called it F1 because it was along the length of the member, and that particular direction we had introduced a coordinate system X1, and therefore we call that as F1. Now it's a moment, so this torque T can be called as an M1. So if the moment is about x2 axis, we will call it M2. If it's about the x3 axis, we call it M3. That's how, just like a force is a vector, the moment is a vector, and its direction dependency is taken care of by the subscripts. And we denoted the force by a single arrow. The moment or torque will be denoted by a double arrowhead, as you see over here, right? So which follows, of course, the right-handed thumb rule, which means that if this is the direction in which the double arrow is, that means the torque is essentially going in the direction of the other four fingers. So the thumb indicates the direction of the vector, and the other four fingers indicate the direction of the actual moment that is involved. Now, coming back to the rest of the geometry, in this case, as is the case with most torsional members, we will use a circular cross-section. And this is because the kind of examples where you find such torque is mostly in shafts, which could be drive shaft, for example, driving from an engine to some other location. A very common example is, of course, from the main gearbox or MGB to the tail gearbox TGB of a helicopter. You will have a shaft running through the tail boom, which is one of the major shafts which is used in flying vehicles, but there are many other examples as well. The other case where it's not such a dynamic kind of torque, but it's also still there and still weaker dependence on time is the wing box, where because of the pitching moment and also the location of the aerodynamic center at which the lift and the drag act being different from the center of twist of the wing box itself, there can be a torque occurring not only because of the pitching moment about the aerodynamic center, but additional pitching moments coming because of the lift and the drag not passing through the torsional center, but instead through the aerodynamic center. So because of all of that, you can have a torque like M1, what we are seeing over here. And how is that wing box composed of? It's composed of the spar webs and the skin. So in other words, you have in the wing that you see over here in the front, close to the leading edge, you will have a front spar. Similarly, close to the trailing edge, you will have a rear spar. And these two together, in particular, they're webs, because the caps are essentially taking the axial loads which contribute towards balancing or the bending or flexure. It's essentially the uh, the web of the spars, two spars, the front and the rear spar, along with the top skin and the bottom skin. All four put together form essentially a box and that rectangular box is what so coming back to what I was saying, so here, once again, we will go through the same set of four quantities, which are used to describe the mechanical state of the structure, namely the loads, stresses, the strains, and the deformation. And then, of course, we'll come back and look at the equations. So first of all, as far as the load is concerned, we just introduced that. That is M1. The main stress that comes out is the shear stress as opposed to the normal stress we had in the previous case. Remember that we had sigma 11 when F1 was there. Here, on the other hand, we are going to have a tau. And that tau will be the subscripts that are there are 1 theta because it's acting on the cross section. So this is the shaft. Then you see that x1 is along the length of the shaft, and therefore the cross section on which the shear stress acts is perpendicular to the x1 direction. So therefore the first subscript is 1. And it's something which is counteracting the torque, which is essentially creating a shear stress which is along the circumferential direction, and which is why we introduced this theta. So unlike in the previous example where a Cartesian coordinate system was more convenient, here it's a polar coordinate system, or more particularly because it's three-dimensional, it's a cylindrical coordinate system that we would prefer. So it's on the one cross section in the theta direction, and therefore you have tau 1 theta, and that is, of course, we'll come to the equations later. That's the stress, tau 1 theta, and the next variable is the strain, is also corresponding shear strain. So as long as you have a composite in the principal material directions, you will not have any couplings, and that is the only strain, in fact, gamma 1 theta, which will be there. And that gamma 1 theta in turn is related to the deformation, and that deformation in this case is denoted by phi. Phi is the rotation in any direction. It's also a vector, but the first particular measure number that we are interested in is phi1, which is essentially the rotation about the x1 axis. So in other words, you're applying a torque about the x1 direction, and which means that the twist will also be about the same x1 direction as the major effect or output of this input, which is the torque. So that being the case, you will see that that is phi1. So we have identified the four variables: m1, tau 1 theta, gamma 1 theta, and phi1. The next step is to relate those four, which is in terms of these three equations, namely the equilibrium equation, the constitutive law, and the kinematics. As far as the equilibrium equation is concerned, once again, it is essentially equilibrating, which is based on the Newton's third law principle. So you will see that the total moment coming because of all the shear stress which is acting throughout the structure has to come out to this. So without going into the actual derivation of this, but it's having a very, very similar construct to what we saw earlier, and we will see in the case of bending as well. So take it from me for now that this is what it is. We will see how some of these things in terms of the actual derivation I may not go through, but we will get into particular aspects of this as we move forward. But this is predominantly coming from a moment equilibrium. All that we have to do is to take the stress. We have to take the area on which that stress is acting. So we know the force. We take the momentum. We multiply by the momentum to get the infinitesimal moment due to that small infinitesimal area. And then we integrate over the entire cross-sectional area in order to get the total torque M1. And once we equate that to the applied torque, we get the equilibration between them. So it's very similar to some of the things that you have done in the statics course, even leave alone the deformable bodies. So once we have that, we are able to determine tau in terms of M1, where R is the radial coordinate. So the farther it is from the center of the shaft, circular shaft that we have introduced over here, the larger the stress that is going to be. And the denominator has a J, which is defined as a torsional constant. In this particular case, where you have a circular geometry, I have shown a hollow geometry, but even if you have a solid geometry, whether it is solid or hollow, it will be given by what you see on the right hand side over here, namely the polar moment of inertia. A lot of people get confused, especially beginners, that J is always the polar moment of inertia. No, it is not. It is only for circular cross sections, whether solid or hollow, in which case you will have this J equal to the polar moment of inertia. Otherwise, there will be a different expression for J, which is a little more complicated. So we will not get into those details. If we had more time, this particular homework would have led you towards that, but this is not for you. So keeping that in mind, J is something which depends on the geometry of the cross section. In the case of the polar moment of inertia, it just becomes the difference between the fourth parts of the outer radius and the inner radius multiplied by pi by 2, and that can be simplified to be obtained in terms of the thickness of this thin-walled shaft. And once we get it in terms of that, we can also put it in terms of the area of that particular shaft. So you can go through this in your leisure. If you have any doubts about this derivation, we can discuss it in the next class. But essentially, we will show that J and therefore Gj is proportional to A bar per 3 by 2, where A bar is not the area occupied by the material, but the area occupied by the center line of the shaft cross section, which may or may not include material. So in this particular example, you will not have material in the hollow portion because this is not a solid shaft. So that it is that area which is important, and therefore that dependence on J is what makes particular shapes more superior for the application over here, right? Now, we have gone through one equation, which is the equilibrium equation. The second equation is the constitutive law, wherein we have to relate the shear stress and the shear strain. So that shear stress is tau 1 theta, that shear strain is gamma 1 theta. And when we relate those two, then we end up with a very, very similar constitutive law. There it was Young's modulus. Here it is shear modulus, which is the constant of proportionality. If taken on in the side of the strain, if it's taken on the side of the shear stress, it becomes the reciprocal of that. And again, we are assuming an isotropic material. Once that is done, that is enough, because in an isotropic material, anyway, there are no couplings between shear stress and any other stress, including the other direction shears. So unlike in the previous example, where we had to also introduce another assumption that sigma 1, 1, when we wanted to say sigma 2, 2 and sigma 3, 3 are set to 0. Here, no such requirement is there. As soon as you say isotropic material, or for that matter, the even a composite, as long as it is orthotropic, transversely isotropic, a particular layer with the coordinate system such that the x1 is along the fiber direction, x2 and x3 are along the direction perpendicular to that mutually, and then we would have the this particular relationship, linear relationship between tau and gamma, with the constant of proportionality involving the shear modulus. The last thing is again a purely geometric relationship, where we are saying that the shear strain, remember, is nothing but the change in the right angle. And we also know that from the definition, even though this is a gamma 1 theta that we are talking about, that gamma 1 theta is equal to its complementary shear strain, namely interchanging the subscripts and making it gamma theta 1. So from gamma theta 1, it's very easy to get gamma 1 theta because they are numerically equal to each other. And so tau 1 theta will be on the cross section, whereas tau theta 1 will be where the circular shaft is cut in a circumferential direction, so that once it is cut over there, on that phase that you would have, on the cut, you would see that particular location over there, you will see that there is a change in right angle on that phase as well. And when we equate those two, you end up with a very, very simple relationship, which is coming essentially from two congruous triangles where you're having certain equal angles, and therefore you're able to relate their sides as well. And that turns out to be the shear strain gamma 1 theta, or theta 1 for that matter, equal to the radius times the rate of change of twist along the length. So in other words, phi1 comma 1, how the angle of twist changes along the length. If that was 0, remember that it is like a rigid body rotation. If it is phi1 is the same at x1 equal to 0 or x1 equal to L and anywhere in between, essentially you're rotating this whole shaft, the entire shaft. Whereas what is happening here is that either you're applying two equal and opposite torques on the two ends, making it twist by different angles at different locations along the length, or you're fixing one of the ends and twisting it, as it happens in a helicopter rotor blade, for example. The pitch controls are all essentially that. In a bearingless rotor, you have it almost like fixed end over here, and then you are trying to apply the torque through a swash plate mechanism, whereby a twist is given, and therefore the angle of attack overall changes. And therefore you have the cyclic and the collective pitch that you deal with over there, which we discussed in an earlier class. So coming back over here, let me just say that now we have all the three equations. So we go about back substitution like we did in the previous example. Now that we have the, because we want to relate always the input, which is the load, to the output, which is the deformation. In this case, the input load is nothing but the torque, and the output deformation is nothing but the twist angle. And in relating that, it's not straightforward, which is why these two intermediate quantities of stress and strain are introduced. In this particular case, the shear stress and the shear strain. And once we do that, the equations become very, very simple. They're dependent only on certain things: geometry, the natural laws, and the material. And because of that, we can now go backwards. Now substitute for gamma into this equation. Now substitute for the tau into this particular equation. So now we are able to relate those two quantities, namely the torque and the twist angle that you see in this over here. So torque is equal to Gj times dou phi1 by dou x1, or phi1 comma 1. So that's the twist rate, which is related. In the previous example, remember, it was very, very similar. Instead of phi1, we had u1. X1 was as it is. Instead of G, we had E, the Young's modulus. Instead of J, we had the area of the cross-section A. And instead of the torque, we had the force F1 acting along the length of the bar or bar column in that particular case. In this case, it's a shaft. So once again, it's along x1, but it's not a force, but a moment, which we call as the torque, and therefore written as T. So in terms of the division, once again, we see there is a material property, which in this case is shear modulus instead of Young's modulus, and a geometric property, which is the torsional constant instead of the area of cross section that we have. And unlike the area of cross section, J does depend upon the not only the size but also the shape of the cross section, and which is why we took a particular shape over here, which is very commonly used. And why a thin-walled circular tube is explained in a simple example that we will see over here, that even though if you take the same material, therefore G remains the same, but if you take two shafts, one is a solid shaft and the other is a thin-walled shaft. This is a solid shaft and this is a thin-walled shaft of the thickness 1 mm, and let's say the diameter is 100 mm over there. In this case, you have a 20 diameter, and the only difference between those two is in terms of how the material is spread. The amount of material is the same. If you calculate the area of cross section in this and the area of cross section in this, it will be the same. And since the length of the shaft is also not changed, it will be one and the same. So the volume will be the same, material is same, so density is same, mass is same, the shear modulus G is also same. The only difference is J is going to be very, very different for these two cases. By using these same expressions that you see in terms of the radius and the thickness, we can prove that it's as much as 50 times. So the same amount of material you're taking, instead of having a solid shaft like this, you are instead putting it as a thin-walled circular shaft like this, and therefore stretching the material out to a much larger radius. Then it's able to take much more torque. Why? Because the stress still is the maximum limit of the material. But since it is outboard, that stress, the moment arm that is going to have for the force acting through that stress integrated over the area is going to be much more now, because the material has been put outward, and therefore the radius is much larger, which is the same as the moment arm, and therefore larger radius means larger moment arm, therefore a larger capability to resist the torque. Because remember, there's an external torque which is being applied over here, and that is being resisted by the shear stress, which is the reaction to this particular action, and that those two have to be equilibrated, and that equilibration is possible in a much better fashion with lower stress values if you have the material outboard, which is why a hollow shaft is much better over there. Okay. Are there any questions so far? You good to go? Can you hear me? Is it okay? Yeah.
Can you hear us?
Yeah, I can hear you now. Yeah.
Yeah, we're good to go.
Okay, thanks. So we finished two examples. We go to the third example, which will conclude all the major examples that we need from the beam. There are a few minor examples, but it's beyond the scope of this course. So we will restrict ourselves to these three examples for the 1D member, which is what we call in general as the beam. Whereas most classical texts will just call this as this alone as the beam, this third example that we are going to do right now. Okay. So once again, in terms of the example is, of course, this spar. So as we discussed, we could have a front spar and a rear spar. You might see some examples of this in the cutout that we have, which you have already discussed, but also in the actual aircraft, which has been skinned out. You can see some of these kept in the front of the aerospace department. When you go for some of your lab visits tomorrow, you could probably take a look at that. Now, coming back, once again, you have four quantities, which are load, stress, strain, and deformation. So let's identify them. So just to keep things a little more interesting, we are taking, instead of the same geometries that we discussed earlier, we are taking a thin rectangular cross section over here, something similar to this, not with rounded edges, but essentially a rectangular cross section like this. Once again, we do the same things, introduce a coordinate system, x1 along the length, x2 along the width or breadth, and x3 along the thickness. L, B, and H are the dimensions of the length, breadth, and height, as always. And this time, instead of what we applied previously, namely M1 on the last slide, here we are applying, you see, M2. So you see the laser pointer over here on the left edge of the screen. You see that what I'm applying is M2. So it's once again a moment, but instead of applying the moment parallel to the length, we are applying it parallel to the breadth. So instead of being along x1 direction, it is now along the x2 direction, and it's along the positive x2 direction, as I have indicated over here. which is what you see as M2 over here, right? So this particular M2, you see the double-headed arrow is towards the positive direction of the X2 axis so that it is positive. Now that is the load that is being applied, that M2, and that has to be reacted in the interiors by the material, and that reaction that we have is what is the stress. And this stress, very interestingly, is an axial stress sigma 11, very, very similar to the one that we had in the first example, namely the axial bar. So axial bar, what we were doing, the load that was applied was F1, which is force, which is either under tension or compression, which is parallel to the length. Here we are applying a moment, but this is also causing a sigma 11. But the mechanism is slightly different, that in this case, at a given cross section, the entire cross section was equilibrating it in a uniform way, thanks to St. Venant's principle being valid. On the other hand, here when you are trying to do a bending about the x2 direction, as you see over here, when you're trying to bend it about this, you see that what happens is that uh, this portion will be under compression, this portion will be under tension, and when that happens, you see that the way the stress is acting on a cross section is not uniform, but some portions are under compression, some portions are under tension, but nonetheless the cross section is having a normal x1, so the first subscript for the stress will be 1, but the second subscript will also be 1 because it's again acting along the length, even though there is no force, axial force being applied. How is that possible? Because the total integration of the tension stresses over the area on which it acts and the compression stresses over the area which acts cancel each other out, and therefore there's no net axial force in a problem like this. In other words, the only reason why those axial stresses are present in opposite directions is to create a moment which is going to counteract the moment which is created by the applied load. So once again, you can either apply these moments on either end of the beam or in a free beam, or you can clamp one end and apply it only at the other end. Then that clamp or the support that you have at the one end will essentially cause that reaction of that particular moment. So it's a pure bending moment problem, a pure bending as we call it. You can also have the actual example in the case of the aircraft where this is happening not because of a tip moment. We are not applying any tip moment over here, but instead what we are actually, it could happen if you have, let's say, a tip engine, then you would have the thrust and the weight of the engine creating that kind of a moment. Okay, so that is also possible, but the predominant case, what you're talking about is essentially a lift distribution, which is actually a force. And that force that you're going to have, that is going to create a moment, which is not only a moment, but also shear force is required in order to resist that, because at any cross section when you take, there's not only a pure bending, but also a shear force coming because of that. So both put together, you don't call that problem a pure bending anymore. You just call it a bending problem. Okay. But in order to avoid complicating things, we are taking a pure bending example. So we have identified, first of all, the moment, which is M2, because it's acting parallel to the x2 axis. We have identified the stress, which is sigma 11, because it's on the one phase in the one direction, partly tension, partly compression. Therefore, it's a function of x3. So in other words, very large value of positive x3, you will have one direction, and very large negative values of x3, you will have another direction. So that's essentially what's happening. So coming back to the same example of the aircraft, because of the lift distribution, you have the top portion under compression. So your sigma 11 that you see over here will be negative at x3 values, which are positive if you've introduced a coordinate system such that x3 is upward positive, and therefore you would have at any location over there, you would see that it's under compression, and therefore your sigma 11 value will be negative. On the other hand, for x3 negative, all the way up to negative h by 2, if the datum is defined at the mid plane of these two top and bottom surfaces, then you would have that particular thing is creating a tension, and therefore your sigma 11 would be positive. So in the extreme cases, you're seeing the maximum compression is happening on the top face, and the maximum tension is happening on the bottom face, and therefore anywhere in between it's actually varying, and it's actually varying in a linear fashion over there. And that particular sigma 11 is what we have indicated as a function of x3 over here. We don't yet know with the kind of data we have presented so far that it is linear, but we can show that it is linear. Okay, so now that is sigma 11 is some function of x3. That's all that we know. And just like in the first example, you told me that sigma 11 can cause not only sigma 11 but 2, 2, and 3, 3 because of Poisson's effect. In this case also it is the same, that you will have gamma 11, gamma 2, 2, and gamma 3, 3. But what we are mostly interested in is in gamma 11. Once again, I'm sorry for this epsilon. It should be gamma 11 rather than epsilon. So we would have gamma 11 over here, and that gamma 11 is also a function of x3, just like your sigma 11 is a function of x3, because there's a relationship between the stress and the strain, which will take care of that. We'll come to that. Coming to the deformation that we are interested in, here is where something very, very interesting happens. Even though we are talking of a sigma 11 and a gamma 11, U1 is not the main thing that we are looking at over here, but U3. In other words, this is bending upwards. And when it is bending upwards, even though at any given cross section, the stresses are in the 1 direction, normal stresses, and the strains are also along the same direction, the major deformation or displacement that is taking place is in the x3 direction. You would have seen, as we've been repeatedly telling under many different contexts, the wingtip can move by the order of a few meters, and that's essentially in the x3 direction along the thickness direction, not along the chord or the span. It is along the thickness direction, and that's what happens. In the presence of both axial and bending, as is the case in the helicopter rotor blade, because of the centrifugal forces, there is F1, and because of the lift forces, there is an M2, like what we are seeing in this slide. In other words, a combination of examples 1 and 3. Then, of course, you will have both coming into picture. Okay. Are there any questions? You're good to go. Okay. So now coming back, so we have to relate these, right? So now is where the equations come in. So once again, it's a very, very similar kind of thing, equilibrium equations to relate this load with the stress, and that turns out to be this. You can see the analogy with the torque that we did in the previous slide. There was a shear stress tau, tau 1 theta, in fact. Instead of that, you have a normal stress here. And instead of the torque that we had there, here we have a bending moment. And instead of the radial coordinate we had there, we have the vertical coordinate x3 over here. And instead of the torsional constant j that we had there, we have a moment of inertia I. Once again, this can be done very, very simply. This can be proven by taking an infinitesimal element. If you take, this is the beam that is bending, and this, let's say for in this example, this is x3. So then what we are talking about is we take a small infinitesimal element over here. We know the stress that is acting is a function only of x3. So within that thin infinitesimal element, the stress is constant. Stress multiplied by the area multiplied by the moment arm will give you the moment resisted by that infinitesimal element on the top. Similarly, if you integrate over the entire cross section, then you get the total moment that has to be resisted, which is the applied moment. So that's the simple equilibration that is done over there, which you would have gone through in the deformable bodies course. And that is essentially leading to sigma 11. I'm just making it a little more precise by giving the subscripts, but essentially you would have seen this as sigma equal to my by I. And here I'm precisely saying which I it is. It is the moment of inertia about the x2 axis is the second moment of inertia, and therefore it is integration of x3 squared dA that is coming over here. So once you carry out that simplification, that integral is nothing but your moment of inertia about the x2 axis, replace it with I22. This is the what the equilibrium equation results in. So once we have that, since the load is specified, namely your M2 is specified, you know the geometry, so therefore you know I22, and at any given value of x3, you can now get the stress sigma 11, right? So that's as far as the first equation is concerned. The second equation, we want to relate sigma 11 to gamma 11, and that is very simply the same equation that we had on the example of the first slide, which is the axial bar column. So that's the constant of proportionality is related to the Young's modulus E. The final thing is once again very similar to what you had in the case of the torsion in the previous slide, where we were relating the gamma 1 theta to the phi 1. Here we are relating the gamma 1 1 to u3. So in this particular case, it so happens that once again gamma 1 1 is of course u1 comma 1. But u1 is related to u3 because the dominant reason why the axial movement is happening is because when you're trying to bend this, there is a curvature that is happening, and that curvature is what causes a particular cross section to shift its x1, and that is related to u3 because of the particular assumptions that we introduced. Remember, in the Euler-Bernoulli beam theory, we not only said plane sections are plane, but also they remain perpendicular. If they remain perpendicular, I can get the data from whichever is easy, namely either the reference curve or the reference cross section, and which is what we do in this particular case also to get to calculate that. We use something very similar in the case of the previous example as well. What did we do there? We said that tau 1 theta equal to tau theta 1, and therefore instead of gamma 1 theta equal to gamma theta 1, the shear strains, because they're complementary by the very definition, and therefore we said that we can instead of calculating gamma 1 theta, which is a little more complicated, we can take the similar triangles that are there and calculate gamma theta 1 and substitute for that. So something similar is done over here, that u1 is known as u3 comma 1 because of that perpendicular to the cross section remaining perpendicular. So a cross section which is initially perpendicular to the undeformed reference curve, once the bending takes place, it remains so initially it is perpendicular as you see over here, and once it bends, it remains perpendicular. So either by the rotation of the cross section or by the curvature, either of those I can get, whichever is easy, and that's how we typically proceed with a lot of the derivations. Which means that the final expression we have for capital gamma 1 1 in this is that it's minus x3 times dou squared u3 by dou x1 squared. So once again, we have utilized the three equations. Now we have to combine by backward substitution. So we substitute for gamma 1 1 into this, and then we substitute for sigma 1 1 into this, which is the equilibrium equation. And finally, we end up with this expression for the input, which is the moment, how it is related to the output, which is u3, the transverse displacement. So M2 is related to u3, and similarly you can derive in the other direction, M3 is related to u2. So in other words, there is a lift distribution which is actually an M2, causing an M2, and which in turn is causing an U3. On the other hand, the drag distribution, the thrust distribution are all causing the moment which is about the x3 direction, which is M3, and that is causing U2 and those two will be related to each other in a very, very similar analogous fashion. Okay, just that the sign convention will be slightly different. Because of the sign convention, instead of the negative, you will get a positive. In fact, on the same slide, I will be talking about that as well. So right now, it's just a single moment about x2 direction, which we call as M2, and the resulting major displacement or deformation that we have on the right hand of this bucketed variables, fourth variable is U3, and that relationship has a very, very similar pattern to the previous two that we have seen, just that the differentiation has increased by one order. In both the previous example, we had a first order partial derivative. In the very first one, we talked about dou u1 by dou x1, that is u1 comma 1. In the second example of the shaft under torque, we talked about phi1 comma 1, which is dou phi1 by dou x1. So both were first derivatives with respect to x1. Here, it is a second derivative with respect to x1. It is dou squared u3 by dou x1 squared, because of u3 being defined as u1 being defined as dou u3 by dou x1, and which is substituted into dou by dou x1, which for the gamma 1, and therefore it becomes a second derivative. It's dou by dou x1 of dou by dou x1 of u3, and which in turn essentially becomes this particular second derivative. But for that, in terms of the overall character, it remains the same. There is a constant of proportionality, and that constant of proportionality involves a material property. Once again, Young's modulus, like in the first example of the axial bar column, and a geometric property. There we had the area of cross section. Here we have a moment of inertia, and particularly it's a second moment of inertia about the x2 axis, which is defined here, of course, as integral of x3 squared dA, which is an area integral, so it's a double integral. And so once again, you can play around with either the material for larger E values, or with the cross-sectional shape with the same area. Namely, let's go for an I section instead of a rectangular cross-section, for example, whereby we can increase the I if the flanges are spread out in the x3 direction. So then you will have a larger I22. If it's spread out in the x3 direction, you would have a larger I33, which is good to resist a M3, which is the moment which comes because of the drag or the thrust. The same moment which comes because of the lift in an opposite direction comes because of the weight, the self-weight of the wing, which is bending it in the opposite direction. So the lift distribution tries to bend it upwards. The weight distribution of the wing tries to bend it downwards. So does the weight of other things which are attached to the wing, like this particular landing gear that you see over here, and also the engine. Those are also going to be downward, but that is also going to create moment parallel to the chord, and the chord direction is what we call as the breadth direction or x2 direction, and therefore that's the moment m2 that we are talking about. The weights are causing a moment this way, whereas the lift is causing a moment this way. Similarly, the drag is causing a moment this way, whereas the thrust is causing a moment this way. So the thrust and the drag are causing opposite direction moments. The lift and the weight, self-weight of the wing are causing opposite direction moments. So they just algebraically get added up. But they are along perpendicular directions. One is along the direction parallel to the velocity, which is the left direction, the drag direction, and also the other which is perpendicular to the velocity, which is the left, and that is going to take the other set of moments. So if we have both together, which is what is the case in the actual aircraft, whenever you have lift, you will also have drag, and therefore, and whenever you have the weight to be carried, you have a thrust also involved. So all these things put together, you will have both these moments that you see on the right bottom portion, where I'm showing the red laser pointer right now. So you will have both M2 and M3. So earlier we were talking of only M2. The new thing that we have introduced is M3. That is the moment due to the drag and the thrust. And once that is also there, it will introduce an I33, But in addition, if the cross section is not symmetric, which is the case you will have in most situations, at the most you will have one plane of symmetry. If it's a symmetric airfoil that is used, then of course your X1, X2 plane will be symmetric, plane of symmetry. But you will never have the other plane, which is your X3, X1 plane, will never be a plane of symmetry because of the use of airfoil cross section. We can't use, for example, a circular cylinder as the wing. It will not generate enough lift, and the drag will be pretty much the same as the lift, and you will not be able to fly, which is why the airfoil shape is so important from the aerodynamic point of view. But that creates a structural complexity for us, not only in terms of the manufacturing, but also in terms of the analysis as part of the structural analysis course, which is why an I23 comes in here, which is the product of inertia. So you see over here that this I23 is a product of inertia. Just like you have x3 squared dA as I22, x2 squared dA will be I33. We'll also have an I23, which involves an x2 times x3 times dA. This is something that you would have studied as part of the dynamics course AE2240. So something which is coming out of that. So this will be non-zero because it's a asymmetric cross section. There are no two planes of symmetry. And therefore, you will have both M2 and M3 related to both U2 and U3. Otherwise, M2 will be related only to U3. If we had a doubly symmetric cross section, M2 will be related only to U3, and M3 will be related only to U2. When both M2 and M3 are present and you have an asymmetric cross section, then you will have a coupling. Therefore, M2 is the direct effect is U3 and the indirect effect is U2, and one of them is involving the moment of inertia, the other is involving a product of inertia. Similarly, the other coupling, and of course, the sign convention has to be appropriately chosen over here. So that gives you the relation between M2 and M3 on the one hand, and U2 and U3 on the other hand. It's not directly with U2 and U3, but the second derivative of U2 and U3. Just like in the previous examples also we saw for the axial bar, it was not directly F1 to U1 relationship, but F1 to U1 comma 1, the first derivative, partial derivative with respect to X1. On the other hand, in the torque problem, we saw, again, it's not a direct relationship between M1 and Phi1, but it's Phi1 comma 1, the first partial derivative with respect to X1 of the twist. So the twist rate came into picture. Here, what we have is not the first derivative, but even more complicated slightly, which is the second derivative. And therefore, here we are talking of a curvature. So instead of a slope, we are talking of a curvature over here. And that curvature is what is the main 1D variable over there. Just like in the previous example, it was the twist rate, the twist per unit length, which was the main thing. And the one before that, it is the axial deflection rate with respect to the length, which was the governing factor as far as the geometry is concerned. Here it is the bending curvatures, and two bending curvatures. One is the bending curvature like this, which is your what you call as rho 2, and the other one is rho 3, which is essentially the curvature about the x3 direction, which are corresponding to your M2 and M3 as a direct effect. But as we see in this equation that we just introduced over here, there's a coupling between M2 and M3 and U2 and U3. There's not only the direct effect over here given by the moments of inertia, that is I22 and I33, but also the coupling because of the non-zero product of inertia, which is primarily coming because of your asymmetric cross section. Are there any questions so far? Good to go? Yeah, okay. The next thing in the same example of the bending beam, we already introduced one complication, which was the other bending moment. But now we can also have the shear force. As I said, the example that we saw over here, we were just applying a tip moment, which is going to be a pure bending problem. But in reality, that's not how the moment appears. It's appearing because of either a lift distribution and or a drag distribution. So it's essentially a shear force along with a bending moment. So it's not a pure bending problem anymore. So it will introduce not only bending stress, which is sigma 1, which is similar to your axial stress, just that it's not uniform anymore. It's varying in the cross section with a particular locations being under compression, particular locations being under tension. On the other hand, once you have the shear forces because of the actual lift or drag distribution and the other weights and thrust, etc., then you will have moment, not only a bending moment diagram, but also a non-trivial shear force diagram. In other words, not zero everywhere. So you will have non-zero values of shear force at some locations, some cross sections. When you have such a cross section or cross sections, then you would have, in addition to sigma 1, you would have an additional stress, and that stress is tau 13. Why is it tau 13? Because you apply a shear force in the x3 direction, and when you're applying a shear force in the x3 direction, the stress is acting on a cross section, and for the cross section, the normal is along the x1 direction. Therefore, the first subscript for the tau has to be 1. And now it is balancing out a force which is coming because of the lift, let us say. Then it has to be in the 3 direction. It has to be either positive or negative x3 direction, but essentially the second subscript has to, whether it's positive or negative, doesn't matter. The subscript will become second subscript of tau will become 3. So that's what you see over here, that we are plotting tau 13 versus x3. So just like sigma 11 is linear in x3, so it is positive where x3 is positive and negative where x3 is negative, as long as your M2 is positive, because I22 will always be positive. So if you apply a positive bending moment at positive values of x3, you will have tension. At negative values of x3, you will have compression, right? Similarly, over here also it's going to depend on x3, and instead here it was a linear dependence, positive and negative at the two extremes, and somewhere in between it is zero. In fact, the way this equation is defined, we have chosen that x3 equal to 0 datum to be the so-called neutral axis, where there is neither tension nor compression. Above it there is tension, below that it's compression for a positive M2, but at the neutral axis itself, it is 0 because x3 equal to 0 over there. On the other hand, the shear stress behaves in a slightly more complicated way. It's a quadratic behavior. In particular, it's a parabolic kind of a distribution, and it reaches a maximum at the center. So it's exactly opposite of this. Sigma 11 reaches its maximum value, either positive or negative, at the extremes, at the outer surface, that is the topmost surface or the bottommost surface. On the other hand, so that's for, of course, for a moment which is acting this way. If it's a moment acting this way, then it's maximum tension or compression at these two end extremes, the boundaries. On the other hand, the shear stress is essentially taken mostly by the material in between. So this is an exception. Remember, when we're talking about Y shells, we were talking primarily about the major loads, major stresses, which are the bending stresses, torsional stresses, etc., which are better if the material is spread outside. Whereas here, you are saying that it is better if you have the material inside. But since this is a much smaller stress to deal with, and it can be dealt with by materials as flimsy as a foam in a sandwich, or a honeycomb made out of aluminium thin plates in the case of, again, a sandwich kind of a construction. So you know that this is something that is much easier to handle, and therefore you still see the advantage of pushing the material outward and putting a flimsier, lighter material in the interior, like a foam or a honeycomb kind of a construction. So now you see that where that goes to 0, this reaches a maximum, and where they reach a maxima, algebraically speaking, positive or negative, this reaches a 0. Why it reaches a 0 is because this stress, remember, we are talking of tau 13. And we said because there are no body moments, because we're dealing with non-magnetic materials, therefore tau 13 should be equal to tau 31. Now 31 is on the face, which is having a normal in the x3 direction, and that particular phase, it's acting in the one direction. So in other words, one stress is coming on the cross section this way, the other stress is coming on the surface of the beam this way, and these two are at 90 degrees to each other, and there should be a moment equilibrium between them, which is why tau 31 and tau 13 are equal to each other. Now on this top surface, if we are not applying any shear stress, then that would be zero, and therefore this would be zero, which is what you see over here marked as zero. But in the actual aircraft, when we go to, this is not a simple beam problem, we will have a Reynolds number which is not essentially infinity. Even if it is large, you will have as a finite value, and therefore there will be some shear stresses. Which may be large or small compared to the inertial stresses, which is what the ratio that the Reynolds number actually determines. But for any finite Reynolds number, you're going to have a shear stress because of the viscous flow as well. You don't have an inviscid flow, but a viscous flow. And when you have such a viscous flow, you're going to have shear stresses on the top. So that shear stress is going to counteract. But remember that that shear stress is on the three phase in the two direction. It's not in the one direction. So once again, you still have an advantage as far as this particular stress is concerned, that it will be zero. And so you will have, of course, depending upon whether there is a sweep, sometimes we might introduce a coordinate system which is along the sweep angle, and therefore it may not even be an orthogonal coordinate system, because remember, one axis is along the fuselage, the other axis is along the sweep angle, so they are not making 0 degrees, but neither are they making 90 degrees. So in other words, you can have a set of axes which are not mutually orthogonal to each other, which might be actually convenient in many cases where you have a swept wing. So the things become a little more complicated, but it's more of transformations that we need to understand. It's a mathematical way of transforming vectors, dyadics, and in an appropriate way. Of course, when you're dealing with scalars, it doesn't matter. So like the energy, etc. So coming back, you will have that boundary condition, therefore it's zero and reaches a maximum over there. And that maximum value for a rectangular cross section, for example, is given by the shear force divided by the cross-sectional area times 1.5. You would expect if it was a uniform distribution, it would just be that force divided by the cross-sectional area, which in a rectangular cross-section is just the breadth times the height. But it's not that, it's about 3/2 times that approximately, which is 1.5 or 50% more than the average stress. And that is what you have to design the interiors for. And typically, even things like let's say foam or honeycomb are pretty good in order to handle that. Okay, now if you just want to compare the magnitudes of tau 13 and the sigma, which is coming over here, sigma 11, for the simple rectangular case, rectangular cross-sectional case, then you will see that sigma 11 max, because the expression is this over here, that's equal to the moment, which is a constant. If the moment is changing along the length in a bending moment diagram, you have to take that location or that particular cross-section where it is maximum. In the case of the aircraft, indeed that is the case, because there's a lift distribution like this, an elliptic lift distribution, and there's an accumulation of the bending moment coming from the tip, which has a zero bending moment, all the way to the maximum bending moment at the place where the wing is attached to the fuselage. So we take that cross section as the one on which M is maximum, right? So we want to find out where sigma is maximum. So here we see that sigma 11 is given by mx by I. So we want to maximize m and x3. We want to minimize I2. So, but for a given cross section, I22 is fixed. So you can look at a particular cross section for which m2 is maximum. and then also at that cross section choose the location where x3 is maximum, which obviously is the outboard. So which means in this case, once again, it is the top surface which is under compression, maximum compression, and the bottom which is under maximum tension. But either one of them in a absolute sense are taking the maximum sigma 11 values. Okay, one maximum positive, the other maximum negative. So when we do that, we see that the value whether for the top or the bottom is plus h by 2 or minus h by 2. So let's take the top, for example, which is under compression, h by 2, and which is I22. Of course, it will have a negative sign. Or you put the in this in any example, you can choose the x2 in the flow direction, and then x3 will become bottom to make it a textile triad, in which case your x3 coordinate system will be having an opposite sign to what we have here. Doesn't matter. Here we are only talking about the absolute values, the maximum, and therefore h by 2 is multiplying mx divided by I2. And the for a tip loaded over here, to take a simple example, instead of a lift distribution, suppose we had a tip load V, then you see that the moment that is going to result is V times L, where L is the length. So this is the force, and which is applied, which is the load. And at this location, we have the force times the distance, which is the length of the beam, and which is V times L. So that's what you see over here, which is the maximum moment that you can have. Anywhere in between, it will be going linearly from 0 to that value VL. Now coming to the x3, we saw that maximum value is h by 2, which is what you see over here. And the I2 for a rectangular cross section is very simple. As you know, it's BHQ by 12, which is what you see over here. The breadth times the height power 3 divided by 12. Once you simplify that, you see that it becomes 6VL by BH squared. Okay. So that's as far as sigma 11 max is concerned. Already we indicated what is the maximum tau. So now we can take the ratio of the two, the maximum bending stress, which is axial or normal in nature, and the shear stress, which is maximum because of the shear force, we see turns out to be 4 times L by H. This was for a simple case where V is a concentrated force at the tip. If it's a distributed force and distributed in an appropriate way, in the case of the wing, we would prefer to take something close to an elliptic kind of a lift distribution. Then you would see that it will be slightly different as far as the coefficient is concerned, but the order of magnitude still remains proportional to L by H. And L, the length, is much, much larger than the width, leave alone the thickness H, which is even smaller, and therefore L by H is very large, and therefore you see that sigma is the dominant stress, tau is a much smaller stress. Of course, some people ignore this tau. That is a danger. You cannot say it is zero. It is small compared to sigma, but it is also present, and we have to design for it. But luckily, it is not as large as sigma 11. Okay, so transverse shear is important only for short stubby beams, because if you have short stubby beams, then what happens is you have something which is not even like a beam actually. The reason why we call something as a beam is because the length is very large compared to the breadth and the height. Now for short stubby beam, the B will not be that, it will be small compared to the length, but it will not be that small. Okay, it might be numerically small, but not in terms of orders of magnitude. And therefore, you would have a short stubby beam. When you have a short stubby beam, you see that this L by H will no longer be very large. And therefore, if it's not very large, then you will see that tau max becomes almost of the same order of magnitude as sigma max. And therefore, you will have to consider that as well, which is what you do for cases like let's say, when you have a delta wing in a fighter, the aspect ratio is not as high as you see over here. For gliders, etc., you will have very large aspect ratio for typical low-speed aircraft, but you go to high-speed aircraft, especially the supersonic or hypersonic, then you have a delta wing where the span is not as large compared to the chord, average chord that is. Then you would, or what we call as the mean aerodynamic chord, then you would see that you no longer can use a beam kind of a model for modeling the wings over there, you will have to make sure that you use an appropriate plate or shell kind of a model instead, if you want to get reasonably accurate results. So I think with this, I complete this slide as well and ignore the homework once again, as I said. So are there any questions? Are we good to go? Okay, I think it's fine. So let me on. Okay, so we were seeing rectangular cross sections, which were, of course, not very difficult to analyze. Now we are looking at sure, yeah, I'm seeing your video as frozen, which is why. Okay. So that's why I was not seeing your thumbs up, but assuming it's there. So I hope you guys didn't have any questions in between.
We're good.
Okay. Okay. So when we come to I section, which is the more common one used under bending because it's much more efficient, you know, you're putting the material where it matters, namely at the flanges that you see over here on the top and the bottom to take the tension and or compression depending upon the direction of the bending moment. Then you see that if you can actually prove that instead of linear, which you had for the rectangular cross section, you will have piecewise linear over here because the breadth is changing. If it's a constant breadth, you would see that it's a single straight line which will govern this. But on the other hand, when we are pushing the material outboard, then we will have this kind of a thing. And once again, you see because of this, you would see that the web, that is this portion, hardly takes any bending. It takes the flange is the one which takes all the bending stress, which is whether it is tension or compression. On the other hand, if you plot the shear stress, which we saw is parabolic for a rectangular cross section, here it becomes piecewise parabolic with a jump over there. Just like here, the piecewise linear had a jump at the interface where the breadth suddenly became large. Here also the breadth becoming small actually makes the stress more over in this particular case, and which is what you see as a jump over here. But in between, once again, it's parabolic, and that's the 1.5 times that we saw for a rectangular cross section. It could be much more in this particular case because of the thinner value of the width over here. TW is small compared to B, and therefore we have a wide flange I section beam. And once you have that, this is how the shear stress distribution in the thickness direction will be plotted versus x3, which is the coordinate about the thickness of the beam. So once again, ignore these homework. So we will just skip that for now. Let me see what I have here. Yeah. So this is the final thing for your course, where remember in the first example, what I called as member one, we derived the relationship between F1 and what we called as capital gamma 11. For now, ignore these. I will come to that very soon. But what we dealt with was a relationship between F1 and capital gamma 11 or U1 comma 1, that is in particular. So then we're talking about the material property of significance is the X modulus, and the area, the geometric property of interest is the area. Then the second slide that we saw today talked about the torsional member shaft, where the material property of interest is the shear modulus, and the property of interest as far as the geometry is concerned is the torsional constant, which happened to be IP, the polar moment of inertia, for only for circular cross sections, solid or hollow, but not otherwise. And most cases we are using rectangular box beams, so never use the polar moment of inertia there. But it's also somehow related to that A bar power 3/2 that we derived over there. So that's what makes things much simpler over there. There are ready formulae to use for calculating the J over there. On the other hand, I'm splitting what we did with the third example, which is for bending, because bending can be in two different directions. In fact, we considered both of them in the same slide. And in the presence of uh, asymmetry, these diagonal terms were going to non-zero. But now, if you have symmetry, let's say, then the simplest example will be just to have a bending stiffness EI2 and EI3 over here, right? So now, instead of considering each one of them individually, we are trying to put them all together, but still in an uncoupled way, because of which we have all these zeros in the off diagonal terms. But in reality, what happens is these also will be present, not only for composites, but even metallic beams. You will see some cases you will have some couplings coming up, depending upon the geometric complications that are there, and or because of initial curvatures or initial twist, etc. Some of these can become non-zero in a metallic beam. But if you have a composite, then more often than not, depending, of course, on the layup, what angles of plies you have chosen, and in which order you're stacking them one over the other. Depending on that, you will see that you can have the couplings coming up. In general, you will have a fully populated 4 by 4 matrix. Now, what are these new variables that I've introduced over here? So let's spend a little bit of time, since we have about 10-12 minutes before we end today. So I need to talk to you about that. So what we are talking about here is, if you look at, so if you're looking at this portion of it, this is similar to what we were talking about earlier, but just that we have introduced some new variables as far as the strain is concerned. Earlier, we were talking about gamma 1, for example. Now that is a three-dimensional strain, as we said, a function of x1, x2, x3, and in a dynamics problem, a function of time as well, right? Now that gamma 1 can be written, once the derivation has taken place, we can identify which are the terms which are not dependent on x2, x3, but only on x1 as far as spatial coordinates is concerned. Then we can identify that as gamma 1, which is small gamma instead of an uppercase gamma, lowercase gamma instead of an uppercase gamma. And that is going to be a function only of x1 as far as spatial coordinate goes. Okay, in a dynamics problem, of course, you will have time t. Okay, and then you will also have the bending contributing to that. Okay, now you might recollect that this equation, of course, it will have a few higher order terms, right? For this particular course, it's enough to see this. You see that even though we consider two separate slides to deal with an axial rod problem, or for that matter, column, when you're considering the case where compression instead of tension. We also considered a different slide on which we introduced bending. Okay. Now, what we're talking of here is the bending curvature. If you remember there, we got the relationship of M2 is equal to EI 22 into U3, comma 22. Okay, so that is dou squared U3 by dou U2 squared. Now, that is what we are referring to here as the curvature kappa 2, not this one. This is what we're talking about here. The bending curvature about the x2 direction, that kappa 2 is defined as u3 comma 2 2, and your kappa 3 is, sorry, 1 1. I'm sorry, over here also I should have written 1 1. Okay, so derivatives with respect to x1. So remember that it was dou squared u3 by dou x1 squared, right? So that's what we're talking about. And here, of course, it's u2 comma 1 1. Okay, so essentially we're talking of two curvatures that are there, which are about the x3 and x2 axis. And remember, see, there's a difference here. 2 is over here and here, right? 3 is over here and here, but this is the correct thing. Kappa 2 is defined as u3 double derivative with respect to x1. Why? Because if you remember that x1 is along the length, x2 is along the width or breadth, x3 is along the thickness. Now, if I have a moment x2, which is along the width, then you see that that is going to bring in the thickness direction a deformation, and therefore that is causing u3. And u3 double prime is what we are essentially dealing with as u3 comma 1 1. Okay, so that's the thing that you have to remember. But the important thing is, even though we considered these two on two separate slides, namely the axial rod column on the one hand and the bending bar or bending beam that we considered on two different slides, both of them were causing sigma 1 1. Both of them were causing gamma 1 1, capital gamma 1 1 and capital small sigma 1 1. So in other words, they're both causing axial stress. In one case, of course, it was uniform axial stress. In this case, of course, we had linear sigma 1 1, right? Linear axial stress. So, uh, but they kind of get added up, and which is what we have shown over here. You see that the first term that I see over here, gamma 1 1, is coming from the axial rod or column, and it is not actually having any x2 or x3 multiplying there. So in other words, it is independent of x2, x3, which is what we mean by uniformity. On the other hand, this is linear. That's why you see x2 power 1 or x3 power 1 over here, multiplying the curvatures over here. Okay, so that is the only thing. We are just trying to combine those uh, three sets of equations that we got. We are trying to put it in the matrix form over here. The third one, which was for bending, we are splitting into two parts, EI2 and EI3. In reality, of course, this will become EI23, these zeros that are there, because there is a coupling as we saw in asymmetric cross sections. So we already introduced one example of a coupling there. In addition, we'll have many more couplings. Okay, so uh, now you see the correlation between what we call as a 3D strain on the one hand with these, which are called as the 1D strains. Okay, so now what I have circled over here is nothing but, what I have boxed over here is nothing but your stress, the corresponding stresses that we are talking about in a stress resultant sense, which is nothing but your axial force F1, the torque M1, the two bending moments M2 and M3. Now, this is what is equal to what I have boxed over here. Okay. And that, if you multiply with the transpose of the 1D strains, you end up with the strain energy density. Of course, you have to have a factor of, if this 2 goes here, it is nothing but 1 by 2. Okay. So then you take that 2 over there. So it's 1/2 the force times the displacement. That is what is your, and even in the case of the spring, linear spring constant, we said that if you have F versus delta, then you have a linear relationship between them. The area under the curve is going to give you the energy. One half of it is going to give you a strain energy. The other half is going to give you the complementary strain energy density. In a linear spring, both are equal in magnitude to each other. On the other hand, here we are talking of an actual strain energy which is building up within the beam or the shaft or uh, column or whatever you want to call it, the axial rod, etc. So in any case, this is essentially what is happening. So two ways of looking at it. One is as a relationship between F1, M1, M2, M3 on the one hand with the 1D strains. The other is as the strain energy density, which is now 1D. Remember, we have talked about 3D earlier, which was joules per meter cube. This is nothing but joules per meter along a unit length of the beam, what is the energy that is going to be. And we have already seen an example of a coupling, EI23. Similarly, in a composite beam or beam of complex geometries, these zeros might also become non-zero. And of course, it always remains symmetric, which means that these zeros can also become non-zero in general. But the main important thing is to identify these diagonal terms because those are the direct effects, and that is what we are seeing in this particular combination of all of them put together. Are there any questions on this? Okay, so with that, I'll probably just finish this slide and we'll be done. So EA is called as the extensional stiffness. Your GJ is the Saint Venant torsional stiffness, which we had derived separately in two separate slides. And the third slide, we had talked about EI2 and EI3, which are nothing but the bending stiffness about the corresponding axis X2 and X3, put both together as alpha, where alpha takes on the values 2 and 3 instead of 1 and 2. So then you have, of course, E as the Young's modulus and G as the shear modulus. So I think with that, of course, in this particular example, the way this is written, the choice for the origin is such that it's at the centroid of each cross section. So at any given cross section, we get the centroid. So for all cross sections, we know the centroid. Then we join all those centroids. If it's a prismatic beam like this, same cross section throughout, then it doesn't matter if you choose for one cross section and just you draw a line passing through that, so that which is parallel to the length, and then you get that centroidal axis. But in general, you would have a situation like this where you see that here the chord is much more, here the chord is much lesser, the thickness is much lesser here, the thickness is much more over here. So there is a taper essentially, right? So that taper also, you could have multiple sweeps as it is in this case till here. You have one sweep angle. Here you have a different sweep angle. It may not be evident from the leading edge, but from the trailing edge, you can see that that is evident because what is important is the line of the mean aerodynamic centers. So you would have all those kinds of changes in the geometry, in the material, etc., along the length. All of that means that you have to appropriately get to the point which defines a cross section and join those points to get a beam reference curve in the undeformed geometry. In this particular case, we are just taking the principal axis which is originating at the centroid, and therefore if you do in this case, because it's a principal axis, you would have your I23 going to 0, and that's which is why you see these zeros over here. Otherwise, if you choose any other axis other than the principal axis, you would have for an asymmetric cross section, you would have I2 3 not equal to 0, and therefore you will have off diagonal terms that are not a diagonal matrix anymore. So with this, we combine the summary of the entire course. This particular slide kind of summarizes everything that needed to be. Of course, I probably didn't have a little bit of time to cover the shell or the beam, but that is what we covered in that entire set of assumptions, whatever we led to in terms of the plane stress approximation, etc., and then brought in the Kirchhoff love theory in the first half of today, pre-lunch session. So there we introduced, instead of these here, remember, these are 1D strains. 1 minute. 1 minute, I'll come to you. So these are, as I said, 1D strains. I thought we didn't do 2D, but we did already. Remember, in the morning session, we introduced gamma alpha beta, the uppercase, as epsilon alpha beta plus x3 rho alpha beta. Now it's equivalent to that. So these are 2D strains. This one. These two are 2D strains because they depend only on x1 and x2. These are 1D strains because they depend only on x1. Okay, apart from that. Just remember this. So that's all that we had. So we have already introduced the same thing in the case of the plate or shell as well. So this kind of summarizes for both beams and shells, which is what you find in a semi-monocoque construction, which is the most common construction for most aircraft today. So with this, we come to a conclusion as far as the lectures of the course are concerned. So if you have any questions related to what we have discussed today or in any of the previous classes or related to your take-home final, I'd be happy to answer.
So I have a question about take-home final. I'm
Yeah.
still not fully sure what we need to put in it again, because you said like the table with 7 columns. That's
Yeah.
one thing. And what else? Because also you said like other concepts from the course. I'm just not sure.
Yeah, so I think that's why I gave you 3 examples of those YouTube videos where you can just see at least that portion where you see the previous batches, what they have done. So what you have to do is to just think of all the variables that you have dealt with in your courses. So the courses that you have done, let's say deformable bodies, statics, dynamics, or any of the physics courses that you have done in high school, all of them will, wherever they're related to materials and or how they deform, then you would have certain variables based on either the content of the chapter or the questions at the end or the homeworks and or exams that you have done. You will identify in each question what are all the variables that were given in the problem, what were all the constants that were given in the problem, and what were the things that were to be determined. Okay, so now you see that you have a whole bunch of variables that you have been giving various names for based on the kind of subject that you've been dealing with. So you have a lot of these different, seemingly different kind of variables, but you can see that they can be bucketed into one of these 4 variables that we talked about: loads, stress, strain, and deformation. Similarly, in order to actually solve that, you have given certain things, you have certain unknowns which you want to determine. If you want to determine the unknowns in terms of the knowns, you have set of equations. Again, the equations that you have gone through in physics and statics and dynamics and your deformable bodies, and also this particular course, structural analysis, you would see that there are a very wide range of variables that we talked about, constants that we talked about, equations that we talked about. Those equations, once again, can be bucketed in terms of 3 sets of equations: equilibrium equations, constitutive law, and the kinematics. So I just want you to think of as many of those variables as possible from as many of the courses, as many of the books, as many of the things that you have been exposed to, either from your own memory or just by perusing some of these notes and or books that you have dealt with or some questions that you have dealt with. Just uh, list out all those variables. Then as a team, sit together and try to bucket them, put them in the appropriate columns for the variables. Similarly, whatever equations you could use to solve for the unknowns in terms of the knowns, you bucket them in terms of these 3 sets of equations. So then you arrive at some kind of a systematic way of ordering these. Start just like what we did in today's class. We started off from the simplest case, we went on to the more and more complicated cases, right? Like building up the complexity of the problem. So that's essentially what I want you to do, to start with listing, bucketing, and then within the buckets, ordering so that you get some kind of a bigger picture much more clearly. And when you're ordering, you will see there are some very similar kind of variables, uh, just that they were given different names or terminology based on where they were coming from. So you can all just lump them together as one set. You can still have them individually, but they all figure right next to each other, adjacent to each other. So that's how I just want you to go about, just to showcase the fact that it's not, things are not as complicated as they seem to be, just because of our terminology, just because of our various subjects that we have separated this whole body of knowledge into. We are seeing that there are so many variables floating around, names for variables floating around, names for equations floating around, but they all actually fall under one of these three categories for equations, one of these four categories for variables, which is what I want you to do. I hope that is clear.
So as in for the last year's cohort, it would be like just 6.1 just the table, because they have 5 different parts as well, with like T-beam proof or something. And
Yeah, so those are the homeworks that I skipped, remember? So if you see over here, I had at the bottom of the previous slides.
yeah.
Yeah, I had, see, homeworks like these, what you see over here. So those are the homeworks that they did, and which you got lucky you didn't need to do, because I did it as a 10-week course for them, with just 4 hours per week. Because of that spread, I could have more time in between for them to do these homeworks, because yours is much more compactly jam-packed. I thought I'd rather skip these homeworks. So just go for the final one. Also, I think I had given one homework to you already, which you have not yet done, which is C44 equal to C22 minus C23 by 2. I wanted you to prove that, right? So I think that still remains. So that's what I was telling to you earlier in the morning class. You can do that as well as the full dress rehearsal on Wednesday. We will be doing it online, of course. And on Thursday, based on my feedback, because I might want you to do something in a better way, or something is not appropriate, I might hint on that on Wednesday's class after your presentation. So when we meet on Thursday in person, you can make a presentation wherein you're talking about including those suggestions of comments, so that you can make it even better than what you present on Wednesday. Is that clear?
So, what was my question was about the tours tomorrow. Tours tomorrow. The
The
trips
lab.
tomorrow.
Yeah, the tours tomorrow. What about that? What's the question?
Tomorrow at 2 p.m., right?
Yeah, no, there is one more at 11 o'clock, which I probably haven't yet sent you the information about. So I'm just trying to finalize that. I'll have to go now check my emails. So I'll send that across. So what would happen is there will be 3 sets of lab tours tomorrow, and one on Wednesday, most probably. So the 3 sets will be 11 to 1, 2 to 3:30 or so, and 3:30 to 5. So that's how we will have 3 sets of visits tomorrow. And on Wednesday, you'll have just one set of visit, which is in the afternoon, 2 to 4. So I'll confirm on all of them. Probably I'll summarize together and put that so that it's clear. In any case, Fanindra and or Prashant and Chinababu, one of these 3 will be going with you, and make sure that you're comfortable transitioning from one to the other. In any case, I'm also giving you the exact locations of those in a Google map. So you should be able to steer through the campus. You also, I think, have a campus map, of which I had given a link for the PDF for those of you who have not yet had access to it.
So tomorrow, what time are we meeting, like the first location? Because you said that somebody will be with us the whole time. So basically the first location.
Yeah. So one of the GTAs. So like Fanindra is there in the class today. So Fanindra, do you know who will be going with them tomorrow, and who will be going with them on Wednesday, so that they will be.
Will be there with them. Tomorrow, Chinababu will be there. For the afternoon
Okay.
session,
One in is it in the aerospace department or where is it?
11 to 1 is also, yeah, I'm finalizing with Dr. Omkar. If
Okay.
it's not Dr. Omkar, it will be Dr. Chausali and Dr. Dabade. That is Professors Rajesh Chausali and Professor Vivek Dabade. So right now, both of them have given 25th as the date. But I wanted Professor Mayurish Patil to look at these because he'll be of interest. It will be of interest to him, both of these. So I'm seeing which of these can be moved from 25th to tomorrow. So one of these, I've already asked Omkar, Dr. Omkar to shift the UAV to 11, but he has not yet responded. So if he has not yet responded, then I will talk to Vivekanand and Rajesh and see if they can have it at 11. So you will have something or the other at 11 tomorrow. And so it could be either Omkar's or Rajesh and Vivekanand's. So all three are at the department. But just that the last one is, even though it's at the department, it's at a different location of the department, which is close to the main security gate. Not the security gate, but the main gate, which is where the old aerospace department was. The open circuit wind tunnel, which you can walk through, that particular thing is located at that end. So it's a fairly long walk. So you might, I mean, those who are able to walk can walk, but otherwise you can take one of those campus public transports.
There is a construction going on around. I'm not sure whether they have shifted it to somewhere else or is it in the same place. The open.
Oh, the OCWT is huge, so I think it will be easy to shift that. It's a building by itself, but maybe there were talks about possibility of shifting it. So just confirm from them. But as of now, I know that it is still in the same place. But just confirm, Phanendra, with somebody else who knows.
Yeah. So Chinababu will be there with them. I will share the contact. So afternoon we will be there with them. Once they reach the aerospace department, from there
Yeah.
he will be.
Okay, sounds good. Yeah.
Prashant will be there.
So where specifically?
Yeah, at the entrance of aerospace. Like, you guys have come on the first day, right? Like if you stay at the entrance, yeah, I give the contact. You just call or message.
Yeah.
Yeah. You give the contact. So he will be there.
You can send that.
Yeah.
All right. Thank you so much.
It's a real pleasure. Yeah, I'll see you on Wednesday, but go ahead with the tours tomorrow.
All right. Perfect.
Bye-bye.
So,
Yeah.
So final question on the take home part. So in class, we like present the table, and then we just put it on a single sheet if we don't fit it in the presentation on a single sheet because
Sure. Yeah.
single sheet of
So you want us to present it as a single sheet, or can it be like a presentation where we cut up the sheet into multiple pieces?
No, I would rather have you as an infinite canvas, zoom into the respective locations and then talk about it. Okay.
We'll do it.
So
We'll do it live. Like we'll cut out pieces of it as a slide, and then like it'll be one thing, but we'll have it when we present it, like cut up.
Sure. So essentially, like what I was showing you over here in terms of the
Exactly.
this. So you have a picture and you can go to the left, right, up, down, and then you essentially talk about one particular thing which you want to talk about. You focus on that and you try to reason out.
Sure. Okay.
Yeah.
All right. Thank you so much.
Yeah, it's a real pleasure. So one of the things, probably I'll talk in a little more detail Wednesday when you're present, but one of the things is I also want you to reason out why you're putting something somewhere. Okay, some of them might be quite obvious to put a particular location, but there are certain variables which are like a kind of compound kind of variables. Like for example, today we dealt with bending stiffness, EI. Okay, now EI is having both a material property as well as geometric property I. If you're putting E and I separately, then you know where to put them. But if you're putting EI as a bending stiffness, then it appears both under material as well as geometry. So there are some things which might repeat. Okay, so I just want you to keep this in mind when you're talking of, let's say, flexural rigidity, which is a bending stiffness or whatever. It involves multiple things. So some of those things might figure in multiple places. So you have to kind of reason out why it is figuring in multiple places. Or if you choose to put it in one particular place, why you choose to put it in one particular place rather than the other.
Okay. All right. Yeah. Is that how you're gonna answer? Like, if you ask us questions, which I mean, obviously you will after we present. Is that how you're gonna? Why did you put this? Why did you put that?
Yeah. So ideally, I would like you to include that information as part of your presentation itself. If I find something is not trivial and you have not explained, then I will intervene and ask a question. So I would rather want you to be complete in yourself in terms of trying to express whatever you think is not so obvious. Try to give a reason for it, why you put it where.
All right.
All right. Thank you. Good evening.
Thank you. Yeah.
Bye-bye.
Oh my God. I don't know.
We can meet late, like 7.